Let us tell you a story about analytics that is going to completely change the way you think about data being collected in the water space, about how one West Coast municipality is driving meaningful improvements in their water organization with Proficy CSense analytics, and is now predicting pump failure up to 16 days in advance. Now, most importantly, we want you to know that the analytics in this story are designed specifically to be repeatable in the water and wastewater space. That means that these proven analytics plug directly into existing SCADA and automation infrastructure that is already there, and then it can scale across your municipality or across your install base with no further challenges. Let me quickly step back to talk about the goal of advanced industrial analytics in the water space. Some say that goal is to reduce energy consumption, to be more sustainable, or to reduce operational cost. Some may think it's to eliminate unplanned downtime altogether, or to improve their maintenance practices. Others may say it's to maintain regulatory compliance, or it's all about optimizing chemical usage. The list goes on, and the fact is, they are all valid goals. But let's briefly move up to a 30,000-foot view and try to just explain what we see below us. We see water moving from place to place through a series of pumping operations, pumping between reservoirs and wells, pumping up to towers, pumping into rivers and lakes. Those pumping operations can be delayed due to things like water treatment or compliancy issues. The processes can be run excessively and end up generating too much water that ends up getting purged in the end. Similarly, those processes can come to a standstill under certain conditions, like equipment failures. Whatever the reason, if you are pumping too much or not enough, or if your water ends up being out of spec, you are simply missing your target. With this simplified view, we can restate our goal, which is to sustainably pump the precise amount of water that is demanded when it's demanded and at specification, while maintaining the lowest possible operational cost. Now that we have established the goal, we are finally ready to tell you our story about how GEdigital is helping our West Coast water customer achieve their goals, starting with a pump failure prediction analytic that can detect catastrophic failure up to 16 days in advance. Our story starts at a point of frustration with the inability to find the solution that's hidden within the mountains of chaotic sensor, maintenance, and LIMS data. Tasks that should be simple, like accurately reporting failures, finding efficiency trends, and correlating those with other activities, turns out to take months to accomplish with using tools like Excel or custom coding. Even worse, the insights that are gained are nearly impossible to act upon because the deeper level analysis that's required would take far too long to accomplish. Things like poorly described problem statements, lack of success criteria, no clear path to ROI, all contribute to unsuccessful analytic initiatives of the past. And at this point, the customer has become frustrated with funding long, drawn-out proof of concepts that end up going nowhere. That's why off-the-shelf CSense solutions for the water industry are designed with a clear path to ROI. They can be delivered with speed and efficiency for quick wins, giving the customer the confidence they need to continue their analytic journey with success. With this customer, we started our analytic journey with two CSense solutions: real-time efficiency with statistics and machine learning classification of pump failure, which can be applied against a number of failures, but in this case, it's applied against a pump impeller bolt failure. So let's take a closer look at the challenges. These are very large Class 3 sewage pumps with internal corrosion problems that can result in major equipment failure. They also run below the OEM efficiency specifications. Corrosion problems tend to manifest around the impeller bolt. As the bolt corrodes and becomes compromised, the thread contact between the impeller bolt and the motor shaft degrades, allowing the impeller to have some wiggle room to move around. When the pump experiences a vibration event caused by some unexpected foreign material in the flow, the already corroded bolt head can snap off. And when that bolt head breaks, further damage to the pump and to the motor above can occur. With absolutely no code, we connected directly into the historical SCADA data stored in their site historians, and additionally pulled in maintenance records from text formats to quickly generate a combined data set in the applied solution. Once the data was pulled in, we were able to use the feature-rich set of tools in the solution to quickly draw out new insights. For example, we found 2 instances of higher than average vibration that appeared to correlate with smaller spikes of data with other tags, such as PSI, flow, or current. Interestingly, this spike in vibration had gone completely undetected in the SCADA alarms because it's actually orders of magnitude below the operating limit. Now, if it were detected when it had occurred, and if the team had taken proper action to stop the pump and simply repair the bolt, had they known about it, they would have been back up and running within a day. Instead, the pump continued to run for 16 days, wreaking havoc on the motor above, ultimately causing that catastrophic shutdown event that took the pump offline for months. The very next step in this analytic process was to visually determine if the data was ready to be used for training the machine learning model. Using additional tools in the solution to mark the failure mode data, we immediately realized that we did not have that good separation needed between the normal data and what we had marked as the failure data. This would confuse the pump failure algorithm. So we took a step to quickly process the data by passing it through a moving average block, and the result was a much cleaner data set that the algorithm would understand much better. Still, to this point, we have not written a single line of code. One of the final steps in this process was to reduce the complexity of the entire algorithm by finding the minimum number of historian tags required to actually predict the failure. Using principal components analysis, or PCA, we found the right tags to use and the right number of tags. But we also gained a new insight. We learned that the failure data, painted here in yellow, was not the same failure mode repeating twice, but in fact was a completely separate failure mode altogether. After exploring these findings with the team, we concluded that sometimes when the impeller bolt snaps, it's possible for the impeller to fall to the bottom of the cavity rather than staying attached. So now we'll be able to accurately detect both of these failure modes. All those processed inputs were then used to train off-the-shelf classification machine learning models, resulting in excellent accuracy for the training data, giving us the go-ahead for implementation into production. And using that exact same solution infrastructure, we were able to quickly plug in the real-time pump efficiency solution, giving the customer much better insight and control over the sustainability and cost reduction efforts that they have internally. If you can relate to this customer story and you are ready to make a story of your own, make sure that you include GEdigital and CSense in your next analytics journey.